What's up, what's up, what's up, what's up? Welcome back. Today we're working on my Git GUI. So I have this guy. One of the many things that he does is he shows diffs of what changed in a given commit. So I can click around, I can see like, oh, here's what changed. And I can see like, oh, there's like some color coding that tells me this thing moved from somewhere else. And if I hover, it should say that it came from a specific spot. Great. So what we want to work on today is there's some cases where this like diff view becomes like overly expensive. So if I say, hey, please don't use more than 50 megabytes of RAM in order to compute this diff, there are cases where it like can't do that. And it gets really bad when I start looking at untracked files, and sometimes there's just like a large file in the working tree, and if I don't limit the memory, then it'll try to allocate like 360 gigs of RAM or like maybe like a terabyte, and all of a sudden I can't do what I need to do. So we've kind of like worked around that by putting like a memory cap. So at the very least now it will like fail in the cases where it can't, but you know, it's still using an unreasonable amount of memory, like 50 megabytes of RAM to not being enough to generate a diff for what is like a fairly reasonably sized file here, like 1,000 lines. Is unreasonable. And so what we're working on is we're working on implementing this like linear version of this like Myers diff algorithm. So let's like, what is this algorithm at all? This is a representation of us attempting to go from a string. Let's see if I can like kind of resize this so it doesn't look like shit. There we go. So we're trying to go from like 1, 2, 3, 4, 5, 6, 7, 8 to 8, 8, 7, 7, 1, 2, 5, 5, 5. So let's maybe pin this on top, and maybe we'll kind of try to write it out in this like second window. So we have 1, 2, 3, 4, 5, 6, 7, 8, and we're going 8, 8, 7, 7, 1, 2, 5, 5, 5. 8, 8, 7, 7, 1, 2, 5, 5, 5. Yeah. So the idea here is that you start with one string, 1, 2, 3, 4, 5, 6, 7, 8, and there's some sequence of edits you can do to like turn this into the second string. So, you know, you might say, well, I'm going to like delete some amount of stuff. Maybe I'll like insert the 8877, and then I'll see this like 1, 2 is the same, delete the 3 and 4, so I have some 5s, insert some more 5s, delete the 6, 7, 8, 8, right? There's like some sequence you can do there. And so what this like visualization is this is saying, well, we have the first string on the top and the second string on the bottom. Or sorry, on the y-axis, x-axis and y-axis. And if the algorithm decides that it wants to take a step to the right, that indicates that it's like doing some action on the first string and not the second string. So that's like a deletion of a character in the first string. And if it goes down, then it's like an addition of a thing from the second string. And anywhere where there's a diagonal, it's kind of saying like, well, these two things are the same. So in our example here, where we went from, where we said we were going to like, delete, where we said we were going to like add 8, 8, 8, 7, 7, and then we were going to see this like 1, 2. That's like the same thing as going down 8, 8, 7, 7, and then we see like a commonality 1, 2. And so the way the algorithm works is he kind of just walks along all of the options on here, but when he sees a diagonal, he immediately says, oh, I'm going to shoot down there. That seems way nicer, juicy. I like diagonals. And so if you just keep following the sequence where he's like walking this tree, where he's like taking free diagonals, eventually you find, oh, okay, so that was the best sequence of actions. The best thing we could do is add this 8877, use the 1, 2 that was already there, delete some stuff, add the 5, use the 5, then delete more stuff and add more stuff. That's kind of what's going on. And so the problem with this is that in order to rebuild the edit sequence that you used to get here, you have to remember all paths that you were looking at on the way up, on the way over. So that ends up being like n squared. So if you have a lot of lines of code, you need to like in your diff, you need to remember a lot of paths, and that ends up taking up a lot of memory. And so there's this like version of the algorithm where you can do the same walk, but you can just not remember the way back, which is fine. You figure out how to get there. Like you figure you did walk the correct path, but now when you get there, you go like, how did I get here? I don't know what to do. And so the trick here for this like linear version of the algorithm is you can like bisect the graph into like multiple points. And so what you do is you run like the forgetful version of the algorithm, both forwards and backwards. This should be visualizing the forgetful one, but it's not right now for debugging purposes. And so at some point here, they like collide into each other at this point. And then you can say, oh, now I've got like two smaller problems, and I know that this was like an optimal solution because they hit each other there. And so then he can say, okay, I'll solve the first half doing like what we were doing before, and then I'll solve the second half. And that uses a lot less memory, because you don't need to remember any of this stuff. You don't need to remember any of this stuff. And you can like keep breaking down this problem until it becomes cheap, essentially. And so this is where we are right now, where we have this like visualization of it, which kind of like indicates that the algorithm is working. And where we ended up last stream was we were trying to convert this back into like a diff that you could look at in somewhere, and it wasn't working correctly. So plan of action for today is to try to make sure that like that diff builds correctly. And then we have to kind of like extend this concept. Right now we're kind of unconditionally just breaking it in half. But what we should do, I think, is kind of like set a sane memory limit. Like say you say like, don't want to use more than 10 megs of RAM. And then you just break down the problem into chunks that will fit in 10 megs of RAM. That's kind of what I'm thinking. Yeah, so that's where we're at. What about like how GitHub does it where every single file is too big, you have to manually load it individually, just use the more efficient algorithm for that? Well, I mean, I think that like in reality, we should never fail, right? I think that the file should never, like, it should be very rare that it's so large that we can't do it, especially, maybe there is some limit, but I think GitHub's limit is way too low. Like, it pisses me off in some cases. But yeah, I think that we should try to use the more expensive version when possible, because when we, like, picked this intersection point, it's possible that when they are about to collide here, it's possible that they're going to hit in two spots, right? It's going to hit here, but then it's also going to hit here. And it's like, how do you know which one is better? Well, you don't have all the information you need if you've forgotten how you got there. It's like harder. You need to just pick one. And picking one will give you like an optimal answer by some definition of optimal, right? The least amount of like edits needed. But it will not give you what looks the best to you as a person. And so, it could produce worse diffs visually for a person. And so we should try to like limit this as much as we can. Yeah, but we will see. Okay, so where we got to yesterday, or not yesterday, 3 days ago? I think I took 2 days off. Was that we have like this new version of the diff that uses the new and improved, well, the new version of the algorithm that we call linear diff algo, and he just does that, like, he's basically doing what we just visualized. He splits the thing in half by doing like one bisection. And what we found was if we start using this new diff in our unit tests, well, we first saw that it was just produced like crashing. But if I use this new version in our unit tests, I think they all start failing. And so there's like clearly something that we're doing wrong. We know that when we look at that graph that we visualized with like manually, there's something there. We're close, right? It's got the right sequence. It has a sequence that we could build, but it's not doing the right thing. So we have to figure out why that is. So let's maybe start with looking at one single test. So we can like this like swap elements test, and he's crashing for some reason. And here we can say, okay, he's trying to go from 1, 2, 3, 4 to 1, 2, 4, 3. So we can like visualize that to see, does that look correct? So we can go to 1, 2, 3, 4 to 1, 2, 4, 3, and then linear to see like, do we have something to work with? Like, how fucked are we? Boom, boom, boom. So we expect to see him bisect down here. Let's go a little slower there. I don't really like, I clicked too fast. So here, it's because with this 1, 2 is common, he immediately shoots all the way over here. And then he goes down, shoots down here, and then runs into the yellow that moved up. So we should see this section, then this section. Great. So we know that like this is like a possible thing. And we know that we're drawing the backtrack here, so we know that we know the sequence as well. And so now the question is, why is it failing? Where does Git's ability render the diffs in different ways per word, line, histogram, algorithm matter here? Is it the same raw data for Myers diff? I don't, so let's see. Let's see if we can go over to GitHub. I haven't seen this like histogram diff, but I'm kind of curious now. I am curious. So let's say we look at this guy, and here he's showing word diffs here, line diffs here. What's like the histogram diff? Get histogram diff. Oh, there's git diff histogram. Oh, not GitHub. Did I just read GitHub when you said git? Yeah, you did just say git. Oh, I get so mad when people conflate git and GitHub, and then I did it. I'm one of the people I hate. No. We could look. You've got me curious. Do I have the git source code? I do. So we can look at histogram. Oh, I guess we could just run git diff histogram as well. Just take a look. So git diff master histogram. Man git diff histogram. Generate a diff using histogram diff algorithm. Okay. Am I in the git folder? I am. So somewhere they must have like histogram. Git diff learn and histogram option to use a different generation machine installing from JGit, which might have better performance. They must have some. Yeah, here we go. XDF histogram diff. So somewhere they must like switch on this behavior. Do is to histogram diff? Okay, so what's the difference here? What is the difference? XDL do histogram diff. What does this guy do? What is going on here? So he says find LCS, which is probably the same thing that we're doing. Maybe. Let's see. Find LCS. Maybe not. Try LCS. What is this guy doing? This looks similar. What is going on here? So he's saying he's doing a loop. Whoa. How did I do that? If I double click this, I've never seen that before. It's kind of neat. This looks very similar. So he's saying, hey, I'm trying to basically move down some diagonal. Line end. It looks like he's doing a within line diff that I'm not doing, which is interesting. So he's doing like within a line and line by line at the same time, I think. I'm not really sure. I'm like kind of like really, really skimming. And then once he finds result, oh, there is some difference here because he falls back on classic diff if he can't find the LCS. And then he runs his histogram diff, which is probably the more interesting part of this. Oh, he's like doing some sort of like bisecting as well. I don't know. And I'm not going to figure it out quick enough for this to be worth looking at right now. I'd have to take a look at this offline. But surely... yeah, not sure. But it is interesting and good to know it exists. Okay, what was I doing? I was trying to test this swap elements thing. Not a single code comment, love it. I mean, I've always been of the opinion that, like, comments are nice, but kind of, like, I don't think they should be necessary, if that makes sense. Like, there's ways to write your code where the lack of comments shouldn't hurt you that much. And especially in something like these like diff algorithms. Like, I think algorithms in general. Sometimes like it's hard to make sense of. Right? Like if you read like math papers, like they're at least like the one when I read these things, I'm like, they're just using a lot of letters and numbers. Like, I don't know. There's like sometimes I don't know if it like cleanly maps to something that you can throw into a comment. Like sometimes like the math is the explanation. You know what I mean? So I don't know. Sorry for the detour. No, it's all right. It's all right. I could have ignored you if I didn't want to do it. Okay. So why is this guy failing? Cargo, test, swap elements. Tej, thanks for the big raid. Appreciate it. 370 people. That's a lot of people. So welcome everybody. Welcome. I'm gonna repeat intro for anybody who was here before that. I apologize, but critical mass is on the other side of this now, so it's worth it. What we're working on is we are writing a diff tool to assist me with my Git GUI. There's reasons why I've written my own diff tool here. Part of it is because I want to be able to like kind of tune it to what I want. So there's things in here like, let's see if there's an example somewhere. There's an example of me like tracking moves. So like here we go. Like in this section here, there's like blue stuff, and I can see like in my diff overview, there's like blue and yellow, and the blue and yellow means that there's movement from one area of the code to the other, and I can even like look at this and say, oh, this is where the code came from. And that's very useful when I'm reviewing some people's, like when I'm like reviewing coworkers' code, it's a lot easier to like review when there's stuff like this. And so I wrote this diff tool. He's using Meyer's diff algorithm. So the idea behind the algorithm is, let's see if we can bring up an old example. Hold one sec. Okay, here. So we visualize this like diff as a 2D graph that represents deletions and additions. So if we're trying to go, in this example, we're trying to go from 1, 2, 3, 4, 5, 6, 7, 8. Maybe we'll kind of slap this always on top, and then we can write mvim down here. And we can say, if we're trying to go from the string 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, there we go. And we're trying to get to 8, 8, 7, 7, 1, 2, 5, 5, 5. You start with this one, and there's like some sort of like sequence of things that you can do to get to the second one. And if I kind of like eyeball this, I kind of want to say like, well, I want to go like insert 8, 8, 7, 7, and then I can like see this like 1, 2 stays between the two. So I like start deleting here, and then I see like there's a common 5, and then I like delete the rest of that as 5s. And so this like 2D graph representation of that problem is basically saying I put the first string, the one I'm coming from, on the x-axis, and the second string on the y-axis. And the idea is if I traverse along x, I'm doing something to the first string and not the second string. So that means I'm deleting from the first string, essentially. And if I'm going down, it's like the same thing. It's like I'm doing some operation related to the second string and not the first string, so that's an addition. And the way this like algorithm works is he kind of just walks this grid, and he says, hey, in some cases, we're going to see that like there's a commonality between the x-axis and y-axis. So here we're seeing like 1, 1, 2, 2. And so here he's walking, and he goes, whoa, diagonal. I love diagonals. I'm going to like shoot to the bottom of that. And then we just keep walking, except on the next step of this algorithm, instead of starting from here, where like the like if you were to like trace everywhere in the graph, he says, oh, I'm not going to do that. I'm going to start from like here. And so he jumps like down this way. And you keep doing that. He keeps following diagonals, and he gets to the end eventually. And so he decided that I should be adding the 8, 8, 7, 7 like I did, reusing the 1, 2, deleting the 3, 4, reuse the 5, delete 6, 7, 8, add 5, 5. Perfect. Wonderful. Now the problem with this is, in order to actually generate the diff that you want to look at as a person, you need to basically, once you've figured out which way was fastest, you have to remember how to get back to the beginning. So like the way that we generate the diff is we actually like walk this path backwards, and then we have our edit sequence. Great. So as the files get really, really large, what happens is you end up using like n squared like memory in order to remember all of the possible paths as you're branching, which sucks. And so what we're working on implementing right now is we're looking at this like linear version of the diff that's in like Meyer's paper. He I think, if I remember correctly. And the idea is you can, let's actually visualize this like forgetful version first. So let's say that you didn't want to use all that memory. You could walk this same path, only ever remembering the last step you took. So that goes from n squared to n memory usage. The problem is now we get to the end and we're just like, no, okay, so the last step we took to get to the end that was the fastest was this step. Not very useful. But if you run it both forwards and backwards at the same time, pretend that we're not seeing the whole backwards path right now. At some point, these forwards and backwards passes are going to slam into each other. So I think it's here. What's going to happen is from this point in the branch, he's going to try to step down, and from or to the right, this branch he's going to go right and down. And so these two areas are going to like, boom, smack into each other. And so what happens is if we pick one of those intersection points, we can now like split our problem into two smaller problems. And then we can just run like the same algorithm that we were running before. But now we only have to remember half the stuff, right? And so you could just break down your problem like this over and over again until it gets easier and easier. And then you're under some like memory limit. Everyone's happy. And so that's kind of what we're working on right now is we have this visualization. We're trying to integrate this new algorithm into our existing diff tool, and our unit tests are failing. So that's where we're at right now. We're kind of like unconditionally bisecting one time at this point. Once we get this one bisection and diff generation working correctly, then we have to kind of figure out, okay, how do we decide when to stop bisecting? How do we manage this like recursive bisection thing? And we haven't really got there yet. So that is where we're at. I hope that y'all are interested. And if you want to stick around, feel free. And I think we're just going to jump back in. Okay, so we're working on this swap elements unit test, and all he's doing is trying to get for 1, 2, 3, 4 to 1, 2, 4, 3. And the idea here is that we're supposed to see, okay, there's supposed to be a traversal that reuses the 1 and 2. Then he should remove the 3, reuse the 4, and add the 3 back. And instead of doing that, he is crashing. Perfect. But we did prove right before you guys got in here that if we do the 1, 2, 3, 4 to 1, 2, 4, 3, 1, 2, 4, 3 in our like visualizer, he does in fact behave sanely. So we have the pieces of the puzzle here. We just need to like put them in the right spots. And so let's start just kind of poking around. What the fuck are you doing, buddy? And what are you doing wrong? Okay. So he constructs his linear diff algorithm. We know that like the stage of the algorithm that generates the diff, this is like exactly the same as what's happening in the visualizer, I'm pretty sure. So I'm pretty sure this works correctly. And probably what's not working correctly is our like stitching together of going backwards. So maybe we can cargo test, oops, not this one, cargo test, and he is logging something. And eventually he's going out of range on our trace. So for context, we've been showing this like 2D grid where we have like X and Y, and we're showing like, some sort of graph like this, boom, 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 whatever, right? The way the algorithm represents this stuff is he represents this in DK space is what I'm calling it. I don't think I didn't really read the paper, so I don't know how they call it. Like, I just kind of like read some blog posts and tried to like gather info that way. But I think they have this thing called D, which is kind of going like down to the right, and then K, which is kind of going this way. So the idea is that K represents how far you've strayed from like this like optimal path. So say A and B were like the exact same file, you would have one diagonal straight down the middle, K would be 0 the whole time, and you would have to like take one step to get to the end. So D is kind of like how many steps you've taken across, and K is how far you've strayed from the optimal. And so we're seeing that like we have some like trace abstraction who like takes D and K and puts them in some buffer, and we're seeing that like I think if I would go back to line 248 here, yeah, we're seeing that when we try to pull some data out of there, he's going like, what the fuck? K, when you're like branching, you should only ever be able to get from negative G to D, and you're like going out of bounds. So what the fuck are you doing? And that's a good question. What are we doing? And so we should look at maybe the backtraced. Rust back trace equals 1. And we can see where this is coming from. So this is coming from the backwards iteration. So we're trying to like rebuild the path that we've walked. And it's at line 147, get move source. Here. Right, so he's saying, where did I come from? What was the last thing I did? and we're passing in some value of dk, and he's passing in d minus 1 and then adjusting k, and he should be something about that is fucked. So we're seeing getting move source for 1 0. So it looks like we started adding some logs the other day for this. Getting move source for 1 0. And if I remember correctly, we looked in the happy path and we saw that k should always be even if d is even. So the idea here is that like you have your d on this axis, k on this axis. And so if we have like d0, he's like this, like the root of the tree, the top left of the graph. And he can go here. For each step, he can branch either left or right. Okay. And so the representation here is that this is k0, -1, 1, -2, 2. And so what we saw is that if d is 1 here, we can only ever be -1 or 1. And if d is 2 here, we can only be -2, 0, or 2. So the idea is that like if d is even, k should be even. If d is odd, k should be odd. And we're seeing that d is 1 and k is 0. So we've kind of like violated that constraint in some way. And the question is, why? So we're constructing a backwards trace here, new Myers backwards for d1, k0. And so it looks like we've just constructed our backwards iterator with some invalid state. And the why is that. So what do we do here? We run our linear diff algorithm and we take out each of like the like subsections of this guy. And we're saying, hey, I want you to go from the depth of the thing that you searched to 0, and I want you to start at the bottom right of the graph that you have. So x, y, yep, those are the right arguments, and here's the trace. And you can convert from like xy to dk by doing like k is equal to x minus y, and it looks like this is fucked up in some way. Looks like we fucked this up. So maybe let's also look at the x and y. Cargo test. And then we can compare this to what we're seeing visually in our visualizer. So this is x4, y4. I see what the bug is. So let's look at the visualizer. Boom, 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 boom. Give it a sec. We slam this a few times. Okay, so if we were to like put indices on this graph, we'd have 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Great. He's saying, I would like to start at 4, 4, and he's trying to convert this into like a dk position, which would be correct if we were looking at the whole graph at once. But we're not fucking doing that. We are splitting this into two subproblems. So in reality, if we were going to put the top left of the graph here, our xy position from this root down here should be 1, 0, not 4, 4. And so I'm pretty sure we have to subtract the area we're looking at. We have to just like say, hey, where am I relative to the top left? So I think if we do algo bottom minus algo top, I think this fixes itself. Maybe? Maybe. No. But we didn't crash. We got a lot farther. So what happened here? So here, let's see if these are both valid edit graphs. Okay, so which one's left and which one's right? Swap elements. So for us, left is what we calculated, and right is what we expected. And so we expected a traversal of 2. We got a traversal of 2. Great. We expected to remove 1, but instead we inserted 1. Then we traversed. So our insertion and removal are swapped. So we expected to go 1, 2, 3, 4. We expected 1, what? So traverse 1 and 2, great. Then we expected to remove 3, traverse 4, and add 3. And what it said was traverse 1 and 2, add 4, traverse 3, delete 4. So I think these are both valid graphs. Let's look at the visualizer again. And so what it's kind of saying is we took this path downwards, and probably if we were to run this without the linear version, it probably takes the other path. Yeah. Okay. So he's kind of saying, hey, I'm expecting you to go right here, and you went down. And this is just a result of us picking one of these two by some rule set. We're picking the bottom left one. And I guess probably a more consistent with the old way would be to pick the top right. Because we prefer deletions over insertions because, well, I just did that because the blog post I read said that we should. But I think that the justification behind that is when you're looking at a diff, it might make more sense to you to see I removed this and added this instead of I added this and removed that, because like maybe it makes more sense to, like, the addition might make more sense in context of the removal. You could probably argue both ways, but I think that like generally they trend towards deletions first. So probably we should just trend toward deletions first as well on our side. Which probably means that when we reconstruct this guy, I'm not going to make an argument whether or not that's better or worse right now. I think that we should be just striving for consistency at the very least. And so I think that all we have to do is when we try to figure out how to stitch these guys together, which is going to be backtracking. This seems relevant. Linear diff algo. Oh, it's in the function diff. Yeah. So here, when we're backtracking, where do we pick? Where do we pick? Oh, it's when we generate. It's when we collide. When we collide with the forwards and backwards passes. So it's snaking. They call it a middle snake. So it's here. Yes. Here we compare the forwards and backwards passes. And so here, I think that if we just reverse the iteration order here, to go instead of going from bottom left to top right, we go top right to bottom left. I'm sorry. What the fuck is going on? Why is it jumping me around? Fuck off, Vim. What are you doing? I don't know what was going on there, but it might have been a bug. So here we're iterating D. Somewhere we need to iterate K. For K and negative D to D. Yeah. So here, I think if we just rev here, does that not work? Why can I not reverse this? Hello? Exact size iterator is not implemented for range inclusive i64. Have I not done? Is that really not something you can do? Does it work for non-inclusive ranges? Am I high? Oh, maybe you need to rev then step by 2. Maybe it'll be okay with that. Yeah. So it's the step by. He probably converts one input iterator to an output iterator, and he doesn't guarantee that the output iterator has all of the same like constraints as the input. But if we reverse the input, then okay, that's fine. So now if we run this like linear version, we do see that he favored the right path here, which is good. We do still see that it's valid, which is also good. Like, it's still generating the same diff. And let's go back to our like other test case that was longer. This guy here. So maybe we should slow down there. And maybe I should like write down what's happening here. So here, before we were picking this bottom left one, and now it should pick this one here instead. Oh, it picks this because it consumes the diagonal as well. Yeah, okay. So I think that this is still reasonable and valid, and maybe more in line with what the natural, like the non-split version would take. So let's look at the same test again, but without linear mode, and then we can compare. So spam, 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 spam. My tendons are gonna hate me for this. But yeah, I think that this is now the same path, and before it wasn't. So looks valid, and let's run our test. Swap elements, and he should pass now. Nice. And if I run cargo test, do all of them pass? No. But a lot of them do. So now we're at 3 failures, and these failures might be reasonable failures. So let's look at replace grow. Replace grow. And let's see, what is he doing? So he is trying to get to from 1, 2, 3, 5 to 1, 2, 4, 4, 4, 4, 5. Okay. Sir, I've smoked some weed and am now munching. Okay, great. Thanks for the update. Maybe you don't have to update us every time you smoke weed, but one update's okay. Okay, 1, 2, 3, 5, 2, 1, 2. How many 4s is this? 4 4s. So we can do cargo run with our 1, 2, 3, 5 to B is 1, 2, 1, 2, 3, 4, 5. Something like this. I'm actually not positive that was right. So let's... Oh god, it's printing stuff. Oh god. Oh god. Oh god. How do I make Vim eat this shit? I guess I just can't. So what were it was replace grow. Control L. Ah, nice. Good eye, good eye. Oh god. Ow. Oh, it's every time I alt tab. God damn. Okay. Kill %2, and then we run it again, but with dev null, and then an ampersand, and then we can look at it. Okay. And then I guess we want to look at the linear version as well. Okay. Oh. Okay. That's interesting. Super interesting. So we are actually hitting some fucking edge case here. Nice. I love that. Okay. So where is this coming from? This is coming from... Yeah. GUI, I don't care. GUI framework shit. Snaking state here. So this is it. We're stepping through the algorithm, and we're looking at snaking state step 351. I guess maybe this is one of those cases where using GDB makes sense. So we can say Rust GDB target debug diff viz, and then I think it's args here to say everything else just pass into the program. No, he doesn't like that. I could have sworn that this is a thing you could do. Maybe it doesn't work with Rust GDB and only with normal GDB. No. Am I high? I thought that you could say, hey, GDB, could you please use these args? I guess why am I defaulting to Google? Let's man GDB. Args. Oh, you put the program, then the arg list. I see. So it's args like this. Much better. Okay, and then we can break it Rust panic. And then we can run. And then we can boom, boom, boom. And we can look at what is happening. Okay, so set pagination off, so that this doesn't fucking pause every time there's a long backtrace. I have a scroll in my terminal. And we're at frame 7. And then I think what's the line for context? Frame, no. How do I always forget this. GDB get context lines. Not frame. It's not what I'm looking for. Info registers list. That's what I'm looking for. There we go. Okay. So we are here, and we're seeing that forwards is not equal to backwards, so we can look at self forwards, d self. No? Oh. I have to print it. Of course. Okay, so we're having the depth of backwards and forwards is different. And why would that be the case? Because these guys should have taken the same amount of steps every time. Does this guy have D3, K3? Okay, I guess there's got to just be a bug in there. There just has to be a bug in there. So we look at the struct linear diff algo, and every time he takes a step, he does the snake step, and he says, "Hey, could you move forwards and backwards?" So it must be that like this step must be breaking out early. So D incremented finished. I guess it would make sense to like log the state of each of these guys. So maybe we'll print out the action he took. So he'll say K incremented, key D increment, and here he's donezies. Okay. And maybe here we'll also print out forwards and backwards. Okay. Okay. Boom, 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 boom. Okay. So here he's going to not print anything because we redirected our standard output to dev null, like fucking idiots. So forwards, I guess step. So here he's probably logging D and K. So forwards, he goes from 2 to 3 to 4 to 5, which is a fucking bug. Ah, it's probably like consuming a diagonal somewhere. We're probably flagging this wrong. Yes. So here, we actually have to avoid incrementing D in whatever the fucking case this is. What is this case? Why are we doing this? Each level of the algorithm works blah, 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 translation of outer loop, blah, blah, blah. If we've passed the above condition, we are outside the region of interest. So we may still need to mark this location in the trace. The next stage of the algorithm. No need to advance diagonals, though, and no need to pause the algorithm here. Can we... Where... I need to look at it. I need to see it with my eyes. So it's here, probably what's happening is he's going off the edge here and saying like, man, I don't give a fuck. And that's resulting in D getting incremented twice. But here, he is not hitting that case as aggressively. Probably related to the fact that the X and Y axes are swapped when we're going backwards. Probably. So I guess here, we just probably right here, we just have to make sure that if we're in the case where we're incrementing D twice, we correctly flag that. So why are we doing it this way again? Let me look at this. Why does this matter? Because, right, we're looking at the data for D values in both directions. And so if that D value is not valid, looking at the data in there is going to give us unexpected results. So that's why this assertion's here. And so I guess we do just have to make sure that these guys work in lockstep. Or we could handle the case where the D values are different. what does that look like? So here we're comparing. What are we comparing here? We're saying, hey, here you were at some step of your algorithm. Did we collide? Yeah, so here he's saying, hey, did we pass each other? And if we did, we need to like convert that into some point. And so we could, the D value doesn't really matter, I guess, other than that the K values for the backwards algorithm won't line up. But we already handle that where we say, hey, is our K value right? Okay. I think I'm drawing the picture in my head. Okay. Hold on. So we have like boom. Maybe drawing a grid is shit. Can I screenshot the grid instead? Yeah, let's do that. Export to color paint. And I need orange something. Sure, that's fine. So the idea here is that we have like K0 is here, K -1 is here, K -2 is here, K -3 is here. So the if we have K0 here going forwards, this is going to be K0 going backwards. And so if we're trying to compare these like diagonals, which is like what the algorithm is essentially doing, we need to do some conversion of like forwards K space to backwards K space. And I guess if one of these algorithms has gotten farther ahead in like what their valid, like the valid K range is, that's maybe fine as long as we correctly handle that. And it looks like we're kind of handling that already. We're kind of saying, hey, if our backwards K is like outside the valid range, then like fuck off. So here we can use the backwards D value when we're like extracting values from the backwards version of the algorithm. And then maybe this assertion just goes away. So this is using forwards DK, then he finds like the equivalent backwards K. If the backwards K is out of range, then he says fuck off. Then we use the backwards DK. And then we check if if we've like run past each other. There's something a little odd here about the fact that they're not running in lockstep still. I'm still not sure that that's correct, but we can maybe try this and just kind of see how it looks. See how he looks. Oh, Jesus Christ. So he just picked the very end? So we actually gain no improvement from this? Surely this is a bug. Surely we should be picking here or here. So it looks like whatever we just did there wasn't valid. Right? Like we would expect... Oh, wait, hold on. Oh, I see what's happening. So I think what's happening here is on this node, is he just shooting down to the bottom, like just because he knows that that's the only path that he could take? Because he's already gone all the way to the right? Okay, let's run this in forwards mode and just see what happens. Hold on, I'm kind of curious now. Boom. No, that's not what's happening. So he's not just like bump in one step. But I do think it has to do with him being on the right side here. Okay, so what is this? What is this exit condition here? Calc x without diagonal. So what is like my next position? My next xy. And then he says if our next xy is out of range of the box, or if it's in range, we continue on. Otherwise, we just skip this step, kind of. Maybe it's not related to this. Where was our... Somewhere we had this, like, log that kind of helped us out here. I want to go back to the failing state. So can we undo these changes? Leave that debug assertion in. Maybe we leave these logs in, though. Yep. Yep. Okay. We'll go back to the state. Okay. We will go back. We'll give him a look. Boom, 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 boom. Okay. So here he said, I'm going forwards. I'm going to 2, 2, 3, 3. So we're seeing K increment logs when D is incrementing. Why? Why? Oh, it's because he's on the edge, probably. I see. It's something like... Where were we? I think I'm almost positive that it's because this loop needs to exit early in the case where we're about to increment D. So here we have to say, like, if self.k, we have to do this like same check. Even if we're out of bounds, we have to say if self k is greater than or equal to self d, we have to return D incremented to allow the upper level to do its comparison here. That sounds right to me. Maybe? Then they'll stay in lockstep? Maybe? Hell yeah. Okay. Sick. Okay. So is this now the same path as the nonlinear version? I can't resize because he's dead, but he's in the background. But we can at least still compare here. It's hard to see the colors, though. So I guess maybe we have to BG and BG5. He doesn't like that. He crashed for some reason, but I think that was the same path. We can run our cargo test again and see if that helped. Oh! They're all passing now. Hell yeah, baby. Hell yeah. So I think that means, since all of our tests are passing, we should be able to say diff new is now the real diff, and diff old is the old version, the old stinky version that we don't care about. And we should be able to run a diff tool. So I think we had diff-u a.text b.text. Invalid context length. Oh, is it lowercase u? Here we go. Okay, so we have cat a text, cat b text, and a is 1 through 8, b is 4, 5, 6, 8, 1, 3, 2. And it looks like if we look at like a regular diff tool, we see this. And if we run cargo run bin spiff a text b text, so we're running our version with the new linear algorithm. If I think we should see something that's very similar. So we should see -1, -2, -3, 4, 5, 6 continues on, -7, and then 1, 2, 3 is added. There's like some bug here with the rendering of like line numbers here. It looks like if there's additions at the end of the file, we stop rendering out like the line numbers, which is what like this stuff on the left is supposed to be. But it does look like that's like a valid diff, which is a very, very good sign. And I think, if I remember correctly, we disabled some shit the other day. How do I, like, we can look at somewhere. I think we turned off some useful code. Here, we did like an and false at line 190 of lib. So let's just double check. Let's just go back and make sure that we undo that. That was and false. Here we go. This was like disabling move tracking. Because it was like fucking broken. We just wanted to see like some form of progress. So let's just make sure. Oh, hell yeah, brother. That's so sick. Now we're seeing that the -1, 2, 3 was added back at the bottom. We're seeing like the tracked move. So if we run spiff GUI on this. We're using the linear version of the algorithm. He's bisecting, and we see like this like. Oh, that's interesting. Oh, because the 1, 3, 2 are in a different order, so they're actually saying that these are 3 different moved segments, even though they're like a very similar clump. That's sick. That is sick. Hell yeah. Okay. I'm so happy. I'm so happy. Okay. So I think we're kind of at the point of now where we've kind of like proven everything works. And now all we have to do is recurse the like splitting up until we hit our memory limit. So let's see. So in our diff library, we have this function diff, and he takes in a maximum memory size in bytes, and he wants to do something with that. And so he passes it into like this like linear diff algorithm. That seems reasonable. This guy should be responsible for deciding how many times he wants to split himself up. Okay. So here, what he should be doing is let's think about this. He wants to try to create the normal algorithm with that much memory, and if it fails, then split it up. So this unwrap is like where we need to like adjust this. So probably right now, we need to construct some test case. We need to construct some test case that will trigger this. Right. And I guess that means that maybe in our visualizer, we'll construct this guy with a really low memory limit. Yeah, I think that makes sense. Because then in the visualizer, we'll be able to see how many times it gets split up. Okay, so let's look at diff viz main. And we can just maybe say we'll allow the user being me. I don't know why I'm calling myself these like fucking project manager terms. The user. I'm gonna pass in the max memory bytes. And here we'll say I'm going to set the max memory bytes to IT next. So we need to create some value. Let mute max mem. What would you call it? Max memory bytes is equal to. Maybe we'll provide some sane default of 100 megabytes. And I would usually say that multiplying by 1024 by 1024 is like maybe not the best way to do this. Maybe it makes more sense to say like, how do I say this? Sometimes it makes more sense to make some constant for the multiplier, but I don't fucking feel like it, and you can't make me. I guess really this should be. We need to convert this to a string. Maybe. This is stupid. But it will make it so that we can like parse the thing later a little bit more easily. Maybe what we'll do instead actually is we'll make this none. Yeah, I like that better. This is none. Then we say, hey, we have a value and we haven't parsed it yet. Oh, we don't even need to write sum here. It automatically is sum. Then we can say max memory bytes is equal to parse arg max memory bytes. And he'll try to pass it as a use size, which is fine. And he's got like the nice little log message telling us that like what it is, blah, blah, blah. Max memory bytes gets pushed into our like argument struct, and we say you are max memory bytes of use size. I guess we say this is optional too. No, we'll just unwrap it here. We'll set the default. So we'll say let max memory bytes is parse argument unwrap or 100 times 1024 times 1024. There you go. 1024 squared. I mean, I think that yes, that is better by some metric of better, but I think that like really it's like I want to know like the purpose of the number. I'm kind of like there's like a people get mad about like magic numbers in general. I'm okay with magic numbers to some extent, but like 100 times MB to B is like more clear about why I'm multiplying by 1024 twice, if that makes sense. But again, I don't care right now enough to do it. But I've spent more time talking about it than it would actually take to do it. So now I've kind of like ended up in this scenario where I'm wasting more time than it would have taken to just do the right thing. And this happens to me all the fucking time, where I'm just like, I don't want to do the right thing, even though it's faster, and then I hate myself for it like 3 minutes later. But we're going to repeat the pattern, and it's going to happen to us again. Here now we are going to pass in the maximum memory from the arguments. Yep. So here and here. And we're chilling. So now we should be able to set like an insanely small limit on our visualizer. Max, max memory bytes, that's what I called it. And I should add that to help actually. And linear's not here either. Linear, run it backwards and forwards. And then we said max memory bytes is memory limit. Memory limit. Okay. So we should be able to diff viz, and let's just set like max memory bytes of like 5. So that should crash. Nice. I actually want to run the linear version, and let's just crank this up to like, 100 and see if that works. That doesn't work. What about like 500? Is it really using that much? Wow, that's crazy. So even like 500 bytes is not enough for like what is quite a simple graph. So that's good. We can just use 500 as our test. That's great. And so this is crashing at diff algo new, like we expected at line 399. Which is here. Okay. So I guess we have sneaking and backtracking states. And I guess we'll say if off rip, we can construct this thing. If we can construct this thing full forwards, we immediately go into the backtracking state. With the full box. So we say that our inner is a linear algo state backtracking. And we have algos, only has one of them. So we're just going to say we are a new vector with our single full forwards algo. Full forwards. And the current IDX is 0. We are iterating our first and only thing. Otherwise, we instantiate our new forgetful version of the forwards thing, who doesn't have a memory limit. And the backwards guy, he should actually be using the forgetful trace as well. Just since we're actually in the area of doing it right. So this guy says, I am forgetful. Okay. So now, I think that if I run this, he shouldn't crash. But I don't think he's going to do the right thing, but he shouldn't crash. So now he's running his like backwards passing. We can see he's like forgetting stuff, which is great. And so then he does his forwards and backwards. Okay, cool. Not forwards, backwards. So he's split forwards. Now, when we like find that the snaking is finished, we found our snake, we need to only move into the backtracking stage if these memory limits succeed. So first of all, we need to save our memory limit. So who gets to own this? For now, I guess this would be owned by snaking state. Max memory bytes. Right. So because once he's past the snaking state, that he expects us to be under the limit. So here we'll say we use a use size here, max memory bytes. And so here he's going to say, hey, am I under the limit? So here he's going to first say snaking state max memory bytes like this, as well as here snaking state max memory bytes. Okay. And so now these will fail. These should fail. So here, if we run this, there's going to be some limit that does not fail on the second half. So let's try setting this up to like 1,000. Oh, 1,000 allows it to make it to the end. So maybe something is lower. 750? 600? Is this... Okay, 650. No, fuck, man. 610. Fuck. It's too close. Okay, but we're hitting these unwraps. And so what we need to do is we need to... Let's think about this. So this is going to turn us into... This is going to give us like 2 sub-algorithms to run. And those 2 sub-algorithms may have different limits. Right? So how do we visualize this? Saying different limits is not what I'm trying to say. Hold on. Let's go back to the state where these guys were using unlimited memory, essentially. Just to visualize. Sorry. This guy was at 500, I think, was where he was. I think. Okay. Right, so here, they've collided, and this box up here is going to require more memory than this box down here, because it's like a bigger thing. And so we kind of have to like say how much memory does this one take up, how much memory does this one take up, and then add them up. And if it's too big, then we're like, uh-oh, that's too much. And so right now we don't really have any like, we just try to construct a thing and it will fail, but I guess we need like a way to calculate the memory usage of each of these sub boxes. Add them up. And really we should only bisect one at a time. Right? We shouldn't bisect both immediately. We should take the bigger one, bisect it, then add them all up, and then do it again. Yeah. Okay. So, the snaking state, he's actually going to have, like, he's got forwards and backwards, and then he finds a snake point. Okay. But he actually is going to want to find many like meeting positions. And he's going to want our algorithms, like he's going to want to like store like boxes, I guess, for each of the areas he's trying to bisect. How do I like draw this out? How do I... Right, because like he's going to start with like one box. Okay. And then he's going to say, too much memory, man. Right? And so then what he's going to do, he's going to make 2 boxes. So he's going to run forwards and backwards on big box. And then he's going to have 2 boxes when they run into each other. 2 boxes. And then he's going to say, too much memory, man. Then what? Then he's going to say, pick bigger box, man. And have forwards and backwards for big box. Find new snake point. And now he's going to have 3 boxes. Too much memory, man. I think he's gonna pick the biggest one of those three. Okay. This is starting to line up. So he's always going to have a forwards and backwards algorithm, but where the forwards and backwards algorithm is running from is going to be different. But once he's found that he's under the memory limit, we're not even going to be in this state anymore. So we're always going to have forwards, backwards. But we're going to have to keep track of meeting points. And this is going to be like XY positions on the graph, as well as boxes. Regions of interest. And these are going to be some vector of rectangles, which we don't have like an abstraction for. So maybe we'll say struct rect. Which is fine, whatever, it doesn't matter. X, U size. I think we're using I64s everywhere, so we'll do that. So top, left, right, bottom. And so here is going to have some sort of like vector of rectangles that he's looking at. And we're just going to say that like these guys are tied together. So ROI should always be one larger than meeting points. Indexes of ROIs should correspond with meeting points, e.g. ROIs 0 and 1 should be on the left and right of meeting point 0. Okay. Seems reasonable. And so on construction, the first time, our snaking state is going to have ROIs is going to be one rectangle of top, left, bottom, and right. And his meeting points is going to be empty. Yeah, lines up. And now we just have to say, for each step of the algorithm, what are we going to do in the snaking state? We're going to step, and what is each step going to do? He's going to think, which box am I currently looking at? Which he doesn't actually maybe care about. Right? He's going to have... his forwards and backwards algorithms kind of contain which area that they're looking at. Which makes sense, I guess. Okay. And so there's just going to be like some extra step here that's like figure out which... No, maybe there's nothing to do there. Okay, so he goes forwards and backwards, blah, blah, blah. He says, hey, are we in the state where we found a snake? And so here we just have to say, if snake is found, what's the idea here? We're going to calculate memory usage of all boxes for forwards pass, for full memory pass. If lower than total memory limit, we are done. Otherwise, reassign forwards and backwards, push a rect, push a snake point, move on. And I guess we also have to like adjust rectangles. Adjust rectangles into smaller ones. Okay. So what does that look like? What does that look like? First, we're going to have to pull out some code to calculate memory usage. So here we just have this like required mem bytes, and we just have to split this out. So function calc full trace mem usage given width and height. Which is just this. Womp, womp, womp. Where'd I go? Here. And then we just return that. Okay. We need width and height instead of A length, B length. And down here, somewhere, wherever the fuck we were, wherever we copy paste this from, we can just say that the required mem bytes is calc. What did I call it? Calc full trace mem usage for A len and B len. Yup. Oh, and it's not A dot len, it's A len and B underscore len, like this. Okay. He also needs to remember the number of slots. So I guess maybe we'll call this mem trace mem calc. I don't fucking know. And it's maybe we'll just have it return number of elements here, and then we can do the multiplication externally. What's the best way to manage this? It's like this number of slots calculation is like important for the vector. I could either return both, but that seems kind of silly. I could return number of slots. Calc full trace num slots. Would that do the multiplication twice? Oh, what a pain in my ass. Okay, whatever. Here, we're gonna fix me unhappy with this API. And we'll just say let num slots is equal to required mem bytes divided by stood mem size of I64. Ugh. Gross. Disgusting. Absolutely atrocious. But it lets us move on, so we're gonna do it for now. And I'll come back later and say, Mick, why the fuck did you do that? And fix it. But for now we live. Okay, so now we can say for rect, self rect snaking, where is my fucking ROIs? That's what I call it. Self ROIs map x rect, I guess we'll call it R. Then it's ambiguous when it means region of interest or rect, which is perfect for me. And we're going to calculate the full trace memory usage for the width and the height. And then we're gonna like sum this. Is it iter map sum? Yeah, okay. Let total mem usage equal this. And so our rectangle now needs to have some sort of width and height extraction, which is fine. It's easy. Equal rect function width. It takes itself and returns a u size, I64 of right minus self left, and height is bottom minus top because we're using farther from the top left is bigger number, which is fine. It doesn't really matter. We just have to remember our conventions. Okay. He actually wants u sizes. Does he need u sizes? I don't know. Oh, yeah. I guess we'll fucking u size here. Like this. There we go. Fuck it. Fuck it. We'll come back for better error handling in the future. But as always, I don't care. You know, it's like, it's easy to get like bogged down by like the type neuroticism, but it's better in my mind to just try to get something working and then refine. So we just write shitty code and then we'll come back and fix it later. because we have this really fancy diff tool that'll help us see what we did. Okay. So we have like the total memory usage, and we say, or let like required memory usage, I guess. If let required mem usage, oopsies, is less than whatever the fuck self max memory bytes. Maybe this should say that he's in bytes, and maybe this guy should also indicate the unit. So we'll rename this guy and say mac calc full mem usage bytes, just to be clear, or else I will forget later. And if this, we're gonna do something. We're gonna have to go into like the finished state, which kind of means that like the finished state doesn't just have like one snake point. He's got like a vector of them. So I guess no matter what, we have to like insert the like new snake into the snake point list. Midpoint list, whatever we called it. Mid snake meeting points, that's what we called them. So we're gonna have to like insert at some position. So we're gonna have to figure out which rectangle we're looking at. So maybe we will just say, maybe we'll just write that down at the beginning. I think that's probably the easiest. So maybe we'll say like current IDX or something, and this is like where should we insert our result? So maybe we'll call this like result IDX in the meeting points. Or maybe it should be which ROI are we splitting? I like that. So then we can call this current IDX. I think that's fine. That's like a fine name. Current IDX is a fine name. Which means that like if we find something, we say let meeting point is equal to whatever the fuck we returned before. Okay. And then we like push this into the thing at the right spot. So we say like self meeting points insert at self dot current IDX. We need to make sure you get the right ordered element. So index first, then value. Then here we return self meeting points. Yep. And then we say if we are still going, we need to say that our forwards guy is going to be some new things. We need to like look at which ROI is biggest, which kind of means that we don't want to sum this right off the bat, because we kind of want to like calculate the memory usage for each guy first, but we also have to split the current ROI. Yeah. So self ROIs current IDX, he has to get like split at the meeting point. So we're gonna say like let new forwards ROI is equal to something, and the new backwards ROI is also equal to something. And so how do we like split this guy? So we're probably gonna split out some function that's like split rect at point. So we're gonna say new forwards ROI, new backwards ROI is equal to split rect at point. Maybe we'll even do rect split, because like these rects are very specialized. Does that make sense? Nah. We'll make it a function. Split rect at point, meeting point. Okay. And we also need to give them the rect. So the rect is self ROI's current IDX or something? I don't know. Yeah, sure. Fuck it. Okay. Do these guys need to have parentheses around them? I guess they do. Okay, we need to like define this function now. So we're just going to say like, I don't know, function split rect at point. And we're going to take in a rect as a rect. And he's going to take in a point, which is a I64. And then we're going to return two new rects. And what? We're going to say that the first rect is going to be it's going to be the source rect with its top and are bottom and right adjusted. So rect is going to be top, rect top, bottom, left, right, boom, left, bottom, and these guys need like commas like this, and so we need to just adjust these guys. So the top and left are going to be the same, bottom is going to be 0.1, and right is going to be 0.0, and then the other side of this rect is going to be the same, but it's going to be top, left, and then bottom right is going to be what it was before. Simple, simple, baby. Okay. Function defined here. He doesn't like this for some reason because I didn't put an ampersand on this probably. And then we say self ROI's current IDX is going to equal the new forwards ROI, I think. And then we're going to insert at self current IDX the new backwards ROI. So we've split this guy in half. And I should double check if insert puts it before or after. So it inserts an element at position index, shifting all elements after it to the right. So if I am looking at index 0, I am saying this is new index 0. So I actually want the backwards one to be +1. And does insert allow like length to be passed in? Panics if index is greater than length, but if index is length, then we're chilling, so we're chilling. You know? If we're chilling, we're chilling. So we've now got like these like 2 boxes have now replaced the 1 box, and we've got our new meeting point in here. And so now we just have to find the biggest one. So we'll say let next biggest, let biggest boy, biggest LM is equal to like this iterator, but like take with the max element. Is there, I guess like, there's like 2 options here. Well, I was gonna, no, sorry, brain melting. I was going to say, I don't want to iterate this twice, and I don't want to store all of the results in a vector. So the only way to like get the things that I want out are to like not use these fancy iterator APIs. So we can say, let biggest LM is equal to 0, and let required mem usage is going to equal 0. This is mutable. Both of these are mutable. And we're going to loop over these guys for LM, for mem required in this shit show of an iterator, but enumerate as well, which is like IDX mem required, something like that. We're going to say biggest LM is equal to biggest LM max biggest IDX. We need to store as well. Okay, so we're gonna say biggest LM if the biggest LM is less than the mem required of this element. We're gonna store the biggest IDX equal to IDX, and the biggest LM is equal to mem required. The sum is incremented by mem required, and then down at the bottom now, required mem usage bytes. Yep. Now we have access to like which one is the biggest and how much is required. So if we are less than the required, we do this. Otherwise, we have more work to do. And maybe we'll do less than or equal to. Doesn't fucking matter. But, you know, I think that's like slightly more correct. And now we say, if not, we need to break up the biggest element. So self current IDX is equal to biggest IDX. And then we have to reassign the forwards and backwards version. So we take the ROI of the biggest IDX, and we construct a new forwards and backwards algorithm for that thing. Oh, yeah, I think we're getting there. Oh, baby. Yeah, that feels good. Okay, so forwards is forwards and backwards. Boom. Let rect top, left, bottom, right is equal to this. Maybe you have to clone it, which it probably doesn't have. Fine. We will take a reference to this thing, and then here, all of these guys are going to say rect, 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 rect. Okay. Get wrecked? Yeah, I was thinking that too. I was a piece of shit back not that long ago. Maybe I still am a piece of shit. But I used to play a lot of Dota a few years ago, and at the time, their chat mechanism really let you like go crazy. They would like let you like color your text and stuff. And so I wrote a like stupid little script where if I pressed a button, it would like simulate key presses for generating like wrecked puns that were like rainbow colored, and I would just spam that button every time I shit on someone. And so like in my head I have all these like this like history of wrecked puns running through my head. What a fun. I like the part of video games where I'm winning, which is a hot take, I know, but like I don't actually like the games. I just like the zero sum nature of a game like Dota, where like I only feel good because they feel bad, and I like leaning into that. Which, when I said maybe I'm a piece of shit, it's like no, not maybe. I'm definitely a piece of shit. Oh, but man, yeah, those are the days. Okay, so we have reassigned ourselves to the point where I think everybody's happy. K offset probably needs to be reset as well. What is this like K offset? A len minus B len. So now our K off, like the difference between the forwards and backwards things are related to the box we're looking at. So the new K offset is equal to rect width minus rect height, I think. Who need to be as I64s. And then we'll say fix me as casts are sketch as fuck. I had a WoW macro that chatted, I'm behind you, and then backstabbed. Yeah, that shit's so fun. Yeah. Okay. K offset is adjusted. Does anything else need to be healed here? Max memory, that stays the same. ROIs we fixed. Meeting points we fixed. Current index we fixed. Forwards and backwards we've now fixed. So I think we're chilling. Maybe. So now the only thing is when we exit the snaking state, we need to make sure that we're walking all the algorithms. We're not expecting there to only be 2 now. We're expecting there to be a lot. So if we finish and we have some meeting points, we have to make a new algorithm for each of the meeting points. So we're going to do something like let it is equal to meeting points into iter. And we're going to say let mute algos equal to vec new. And we're going to do the first step where we like populate the algos with one thing. So this is going to be like kind of like vec with a diff algo with using A and B, Y and X, but Y and X is going to be let X, Y is equal to IT next on wrap. Yup. And here we should use self-mac snaking state memory max memory bytes. This is technically not right, but it's like fine because we've already validated that we're under the limit. And then here now we're going to iterate the rest of them. So for X, Y, and IT, we're going to algos push. whatever like this second thing is. So maybe we store these guys as prev x and prev y. Then we go from prev y to prev x. Hold on. With the special cases at the end. Special cases at the end, not at the beginning. So prev y, prev x, we set to 0, 0. We go to prev y, prev x to y x with snaking state max memory bytes. And then we have to tack on the last one. So the last one is going to be prev y, prev x to b len as I64, a len as I64. Yep, and then these just have to be pushed into algos. So let mute algos is equal to vec with capacity of meeting points len plus 1. One more algo than meeting point. We push algos push like this. And algos push this guy. And then I think the rest of the code already kind of works. Here we need to make sure that we assign prev y is equal to y and prev x equal to x. Do you think it works? It might. There's like a non-zero chance. That'd be kind of cool. Fuck. 453 GG. So I guess the finished state can only return a reference because technically it's still using this thing. So we need to do like, we could clone it, but I think it's fine to just kind of like slap on a something like this. There's no reason to get crazy with it, but there's no reason not to, you know, we can preserve it. It's fine. It doesn't matter. Expected I64 found reference. So now when we like use these things, we need to say dereference this, please. And then we can't into iter because he's fine. This is why it's a pain in the ass. Let max memory bytes equal to snaking state max memory bytes. We just to avoid like double borrow bullshit. And then here we use max memory bytes instead of pulling it out of the snaking state. Blah. Blah. Okay. Are we chilling? Maybe. Okay. So here he crashes. Of course. What else would I expect? So he's over memory limit error at 537. So that's interesting. So here we're saying that we finished, but we're still over the memory limit. So somebody is returning in an like invalid state. So here we're saying if the required memory usage is less than or equal to self max memory bytes, what's the fucking problem? Required mem usage bytes. What does he think it is? Are we just like fucking something up? What are you complaining about, my man? My man. So he thinks it's 408, but then we're trying to allocate something that's 624. At what line is this? This is at line 538, right? Yeah, 538. So it's in the loop. What? Diff algo new takes in A and B, and he tries to construct a Myers trace with these lengths. Ah. So this is wrong. This should be right minus left and bottom minus top. And then we can say try into unwrap on both these. Because we're not looking at like the full slice. We're only looking at the part that's relevant to us. Okay. So that should fix that problem. So it goes boom, boom, boom. Okay, okay. Okay, now let's try like really hammering the limit down. Like let's say like what, like 50? So he's gonna hit. Okay. So the limit's actually too low no matter what, which is kind of interesting there. Hey, thanks for the 100 bits. I don't know what bits are, but I think they're like money, which seems cool. So thank you. Yeah, so I think what's happening here is he's failing to recognize this like linear section, basically like immediately cutting parts out. And then he's saying like, I meet here, and then he just keeps creating the same box over and over again. And he's also not like presenting the other boxes that we have available to us. So I think there's like a few problems here. Let's look at the debug info thing. So he's only rendering the forwards and backwards debug infos. But maybe we should maybe be giving all ROIs, even of areas that we're not currently looking at this like very moment, just that like it's like available to us. So I guess we can just push more things here. So we can just say let infos equal to snaking state ROIs map R into some sort of debug info. Yeah. And what does this guy have? He's got these. So we're gonna ignore the fact that there are potential, like, there's a potential path he could be taking. Like, fuck this. This is just an empty vector. But then we'll have our limits passed in, and then the outside should render these. Okay, so it should be our top, our left, our bottom, and our right. And then we extend this infos with the debug info from the actual algorithms that we're running, and then everyone should be happy. So then we should be able to say like, this is mutable, and then we should be able to say like infos extend. Is there no? Oh, he needs to know that he's a vector, I guess. And we can say like extend hello. Oh, we don't, because there's no map. We should say like iter like this. There we go. Extend, and we can extend with this. And does extend, he just like modifies in place, right? Yeah. Yeah, okay. And then here we say, here are our infos. And then I think what should happen now is we should draw boxes for all of the things that all of the like sections that we've like decided on. Yeah, nice. Oh, yeah. Nice, that's pretty cool. Okay, so let's try to set like a less aggressive memory limit. I just want to like see the like happy path. Not bad. Not bad at all. That's pretty sick. So we see this work into 3 segments? Hell yeah. Okay, so let's try with like something bigger. I don't know. Oh, so we're back at the plate. We're hitting this like edge case. We're hitting this edge case, but that's, I mean, even just looking at that is so fucking satisfying and cool. So yeah, what's the bug here? The bug is that it's not guaranteed to get smaller. I guess you need to like, if you're meeting at a diagonal like we are here, you almost want to like take the diagonal out. Because I guess at D0, what happens? You like shoot down this slide. Well, it's not even, I guess like what's, at this point, why is it picking the same big ass box? Really, because first of all, these are meeting here. So there's a kind of a condition where it's like, probably there's, when we're checking if we've met, we're checking less than instead of less than or equal to, is what it looks like there. So can we look for snaking state? And in the snaking state, he's saying, hey, if my forwards x value is greater than or equal to the backwards x value, okay, so why the fuck isn't this happening? Can we like print line can we like look at what these are? Like if I print these, is that gonna give me any like useful, valuable info? Maybe. We'll say here's for this given D. I guess we don't need the D. We just only need the K. We don't need the D. Never forget. We're gonna log the forwards and backwards x values. And maybe this maybe there's maybe like an off by one in here. Seems possible. So here like there's clearly meetings happening here, right? Okay, we're gonna delete these. Getting move new like where can I delete some stuff I don't care about? I don't care about this. I don't care about this. Don't care about this. Don't care about this. Don't care about that. Okay, let's try that. Let's try that. Okay. Blump, 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 blump. Okay, here. So, like, what the fuck? So at k negative 1, that's this line here. We have forwards x 5. What? Oh, negative 1's up maybe? K3, forwards x3. That makes more sense. 0, 1, 2, or 0, 1, 2, 3. 0, 1, 2. So we're looking at this one. Backwards x11? He's right here. Something feels wrong here. I want to see their whole paths. So let's go back to the world where we're not using forgetful Myers traces in our snaking state. So here we'll use a full Myers trace with, you know, just a lot of memory. And we'll do it here as well. Yeah. And these guys are saying forgetful, but they should say full now, and we'll come back and fix that later. But I like it'll help me visualize if we see everything. Help me understand. Okay. Now we crash, which is kind of interesting. Why is the behavior different? Lib 254. This is coming in snaking state step at 416. Oh, that's a good clue actually, because I think the forgetful trace like will let me access memory that's invalid and just like assume. So that's actually a good clue that using this, like, he's saying, hey, I'm out of fucking bounds, man. And so where in this are we? We're at 416. So we're here. And we're saying, hey, I'm trying to look at this dk value. But he's saying that the fucking k value is not within negative d to d? How is that possible? Here our k value is literally negative d to d. What the fuck? Rust, cargo run, will you delete this and say, hey, I would actually like to do something more interesting. I'd like to rust GDB with the arguments provided, target, debug, diff is, and I'd like to bake it rust panic, and I'd like to run this. What? Oh, it's because this is not valid. Okay. Run. Oops, break rust panic. Continue. Okay. So blah 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 blah. What the fuck are you complaining about, man? Set pagination. Oh god. Oh, I hit tab and now it's like, oh, there we go. Pagination off. Okay. Backtrace. Okay, where the fuck are we? We're panicking at frame 7. PK, PD. Depth 0, K negative 5. So this is at 301. Okay, so here we're saying, hey, we are calling get mute. Okay, yep, that's fine. Up. 416. So we have forwards D is 0. What the fuck is going on? Like, is this loop not doing what I think? Like, how is this possible? I don't understand. Because K should be limited to negative D to D. Unless something in here is editing. Fuck me. We need to break in this scenario as well. So here we need to like return snaking state response none or something. So that'll break us out of this, but say you need to fucking keep calling me. Okay. Let's try that again. So now he is... Something else is happening. Oh, because we didn't compile. I'm an idiot. Cargo run. We need to compile for the code to run. Shocker. I know. Who would have thunk it? Okay. So this is working now. That's great. But we're still hitting a problem here. And so what's happening now? We are panicking at 358. So that's here, our height, where our bottom is probably not bigger than our top. I guess we'll just rust GDB again. And we have to break it rust panic. Okay. God, I have to fucking set pagination off. It's so annoying to have to type that every fucking time. I should just stop. I should like put that in some sort of thing. So can we like go to frame 8 and print self? Bottom and right, top 7, bottom 6. So how the fuck has that happened? It must be when we split rect at point. Did we make mistakesies? Top left, bottom right. Top left, bottom right. So how's my... Can I go up one and we can maybe like print out self ROIs? Up? up, 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 up. Okay. So here we have 0, 0 to 4, 7. 4, 7 to 6, 6. 6, 6 to 12, 13. So how the fuck? It's when we split this guy, we somehow ended up with an invalid rectangle. Midpoints, is it called? P self.mid meeting points? There it is. P self meeting points. Yeah, so we found one meeting point at 4, 7. And then another one at 6, 6. What the fuck is going on here? Oh, we need to adjust for the top left. Because the meeting point has to be related to like the top left corner of the box we're looking at. So this is like plus self ROI self current IDX dot left, and this is plus self ROI self current IDX dot top. Okay. I don't really know if that's going to break all sorts of other shit. But at the very least, I'm pretty sure that was wrong. Boom, 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 boom. That's not fucking correct. Right? Is it? Right? This guy's going to go... We're going to get like a line here. It's like it should meet here, if anything. What does it think is down here? You probably have the same bug for the bottom right. Bisected rect. Oh, yeah, maybe. Yeah, it could be something like that. Let's look a little closer. Meeting points. So let's just be very careful about what's happening here. So we have some meeting points. We have to split the rectangle at the given meeting point. So we have the top left and the bottom right. These rectangles should be relative to the right spot. Like these ROIs, these should be in like global space. And it looks like it's like when we construct these guys that something's wrong. Let's keep going. Like, let me double check here. So this guy is fine. It's the ROI that we split out. Okay, so it's got to be like print line ROIs, and we'll just print this out, I guess. Because surely we're doing something fucking stupid here. Surely we're doing something fucking stupid. We should probably print the meeting point as well, actually. This is... We're gonna gain no info out of this. So we can print out meeting point like this. Okay. Okay. Okie dokie. Blump, 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 blump. Okay, so here we found a meeting point at 4, 7, and we split 4, 7. Great. Then we come out here. Boom. We found a meeting point 10, 13. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, what the fuck? Okay, so the meeting point is... They're bisecting correctly based off of the meeting point. But the meeting point is just fucked. So this must not be it. But how could it not be? Forwards xval. from the trace. The backwards x val is from his trace. Oh, wait, hold on. So we have forwards x4, backwards x9, forward x3, backwards x8, forward 6. So we're looking at 6, 5 in that box. And is that actually reasonable? Like, what am I missing where this box is getting 6, 5 as a meeting point? Because in that case, 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5. Oh, sorry. Like wherever 6 following that trail. Like I think that like might make sense. We're not logging the y value, so we don't know where it is on the y-axis. But then like why? Right, like it's very, very clearly here. Is there any world where it does end up over here? No, that's impossible. So there's some sort of like conversion bug somewhere. What's interesting is like these paths are totally reasonable. So it just has to be in like this stuff. Okay, let's log k. Let's log backwards k. Uh-huh. And maybe we even log this unconditionally up here. And then it'll tell us this. Boom, 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 boom. Okay, so what's happening here? We have k for k3 backwards k1. So let's first of all figure out if that lines up. They should be offset by 2, right? Because we do see that there's, if I follow this diagonal, there's 2 more to the right. So that's great. But the k values are 2 offset from each other. For k3, 1, 2, 3, we're looking at backwards k1. So that makes sense that they're both offset 0, 1, 2, 3. I like follow this diagonally is like 1 offset. So that kind of makes sense. And at this case, we have the backwards x value is 9. So does that make sense? 0, 1, 2, 3, 4, 5, 6, 7, 8. First of all, there is no 9. Okay. So that's a good clue. Is that 9 doesn't exist in here. So what does he think that his backwards x values are? He thinks they're 9, 8, and 5. So this would be 8, 7, 6, 5, 4, 3, 2, 1. So what are these 2 that are adjacent to each other? These shouldn't exist. 9 and 8? There's no adjacent x values. Oh, here. These 2 are adjacent. 9, 8, 7, 6, 5. Okay, so backwards x with backwards k of -3, he thinks that we're at backwards x5. So he thinks this is 5, but then where do the 8 and 9 come in? Something about this is just fuck. It looks like the backwards x calculation is just like hella suspect. So here we are extracting some value given a d and k. So maybe we should also print the d value. That seems relevant. Very relevant. because then we can try to infer about what we're looking at in the trace itself. And then we are suspect of this looks suspect to me, actually. This I almost feel like to get the backwards x val. Oh yeah, okay. So we get the backwards x val from this trace in like backwards space. Then we get the backwards. This, yeah, I don't understand what the fuck this is doing. Oh. Okay. So in backwards space, this is x and this is y, and we're trying to convert it to forward space of like fx and fy. And so here we're extracting a backwards x value that's like here. Then we're because their x's are y's. Then we're converting it to say, okay, so what is like the equivalent y value for this, which is x minus k? And then to get the actual x value, then we also have to say, since the y values are going this way and we're trying to get this way, we want right of this box minus how far in this way we are, which makes sense to some extent. Let's look again. Bum, 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 bum. I wonder, actually, let's do one step in the new box, because that actually might give us better intuition here. So here we have forwards x1, backwards x11. Why are we only logging this one time? Because we're iterating twice here. Oh, because they don't line up. Sure. Okay, so we have one diagonal that intersects with itself, which is this one. And here we're saying that our forwards x is 1, which is correct, and our backwards x is 11. So let's look at that. 0, 1, 2, 3, 4, 5, 6, 7, 8. Where's the 11 coming from? 11 is not possible. So there's a bug here for sure. We have right 13. So the forwards x is relative to this corner, and the backwards x is relative to like the whole thing, maybe. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this is 11. Haha, yes. So our backwards, this has to be right minus self backwards left to get offset. Oh my god, fucking fuck. Okay, so this collides, boom, boom. Hell yeah, that makes way more sense. Oh, that's so, oh my god, it's beautiful. Oh, that was perfect. That was very, very good, other than the fact that we still hit this case where like the maximum memory is still too low, so we don't like exit cleanly. Oh, but that's sick. Okay, we need like even more. What if we say like 2,000 here? Oh, that's too much. 1,000? 1,500. I want to see like 2 splits. Oh, that's so fucking sick, man. That's so fucking sick. Look at that. That's beautiful. So here he collides once, collides twice, and then... Whoa, why is he going out of bounds here? Hold on. Like here, he should not be going out here. So there's a bug with our last forwards pass, I think, when we construct these guys. When we get into the backtracking state, It's a non-square ROI. Yeah, I get that, but he shouldn't be going out there. He should be skipping. Oh, that's probably a result of that bug fix from earlier, where we return early. Yeah, okay. I think it's fine. I think it's. Let's see if I can find it. When we fixed that bug where the linear diff needed to be able to stop when we hit the right side, that's probably what we're hitting there. Let's see. So here, if I understand, yeah, it's that bug. So here, what's happening is we needed to be able to stop at the right side of the thing. So because like our D values needed to line up with for the forwards and backwards passes. So what'll happen is he'll hit the edge here, and then he'll shoot all the way over as far right as he can go. So here he's gonna say, I expect to hit K equals 5, so he's gonna shoot 2 out here, which is reasonable. It's like a visualization bug more than anything, so I'm okay with that. But otherwise, that's super slick. That's so fucking cool. So let's try like a very slightly smaller memory limit, just to see if we can like get a quadruple bisect. Oh, that's so fucking sick, man. Oh, yes! Woo! Okay, that's pretty sick. And then can we check if I guess our cargo test won't be very useful because we don't have like the bisecting working correctly. But like, it like works here, but I don't know if it's hooked up to like the full diff. But yeah, I'm pretty stoked on that. That's super fucking cool. That's super cool. We're over the 2-hour mark, so I think it's time to call it. But if you liked what you saw, I stream most days at around 1 or 2 o'clock Pacific time for 1 or 2 hours. There's a YouTube link in the Twitch description where all of our previous projects have gone up, as well as like VODs for what we're currently working on. They usually come out like 1 day after. I'm a little bit behind right now, so I have to upload Tuesday's VOD today, but tomorrow we'll be back on schedule. There's a GitHub link in the Twitch description as well, where code for everything ends up usually in a prettied up state at some point. If you're watching on YouTube, there's a Twitch link in the YouTube description where you can come by and say hi if you're online between the hours of 1 and 4 Pacific time. I stream most days. What we work on right now, we're working on this diff tool, but there's like other stuff in there as well. So we've like looked at operating system. We like wrote a really shitty operating system. We wrote a really shitty neural network. We wrote a shitty virtual file system. There's kind of like a trend here where we write shitty things. We've been working out like what else? 3D, like this like brick maze on the right, the stream intro that's like 3D using OpenGL. There's just kind of like whatever I feel like working on. We end up working on sort of some like web dev and stuff as well. It generally trends towards lower level because I find that more interesting, but like, you know, there's no real limit on what we're gonna work on other than whatever I feel like. So feel free to swing by if you care to again in the future. If not, great to have you this time, and I'll catch you never. But for those of you who come back, catch you on the next one. Bye!